So can you
Yeah,
see
I can
this?
see yours. Yeah.
Okay, great. Let me just do this. Should I just start or?
Sure, please go ahead.
Okay, great. So first of all, just to thank the organizers for giving me the opportunity to talk. I'll be discussing some aspect of geometry and how that shows up for the static model HEFT. And this is based on work in this set of papers here. Some of the papers are more on the formalism side, while others are really more practical in that you get actual calculations with numbers out. But they all rely on this same underlying idea of geometry showing up in field space. So before I start with the main part of my talk, I just want to put some statements out or put some questions out. Namely, what are the fundamental building blocks in a quantum field theory? And you might answer this question in various ways. Maybe the most conventional is to say that we start with Lagrangian, which consists of various fields. These fields transform under symmetries, and you can construct invariant operators. And in an effective field theory context, you can add operators with higher mass dimensions. But there is a fundamental issue with this in that the fields are not have any special meaning by themselves, because you can always redefine your fields. So my set of fields can be different from your set of fields, and hopefully our predictions for physical observables will be the same. And this is encapsulated in what's called field redefinitions. So for example, if you have a scalar field, you can change it with this nonlinear term, phi squared, which has some arbitrary coefficient. And this coefficient would always cancel out in calculations of physical observables. So that there's an inherent redundancy in this description with fields. So a different way of answering this question of the building blocks is to then just skip the whole Lagrangian construction completely and focus on something that's more closely related to physical observables, namely on-shell scattering amplitudes. And this has been the mantra for these modern amplitude techniques, has been developed in recent years. An example of this is that you can look at the non-factorizable part of 4-point amplitude with 2 gluons and 2 Higgs bosons, which was done by Shadme and Weiss. And the resulting amplitude is given in this expression here. So at front, you have this bracket 1, 2, which is a spinor product, which has been discussed in other talks in this workshop. And the rest of the amplitude is parameterized by some coefficients, A1, A2, A3, and so on. And this is a very economical and clean way of just getting down to a simple expression for the amplitude. There's no fields and there's no redundancies in this expression. But you might ask, what are these coefficients, A1? Do they have any inherent meanings, or are they just some arbitrary random parameters you use? So I'll get back to this point on a later part of my talk. But for now, I want to introduce some geometry concepts into the static model HEFT. And luckily, not that many talks ago, Nathaniel talked about a very similar topic for the Higgs effective field theory. And I apologize for not having any fancy pictures, but if you want, you can always look at his slides and imagine those pictures, and they, for the most part, apply here as well. So I will try to answer some questions during the talk. So I'll explain what I mean when I'm using the words a geometric field space. And I'll show some direct consequences of organizing your calculations in this way. And at the end, I'll try to explain why this is a helpful and useful way of thinking. So let's just start with something very basic, very simple, namely the standard model for the electroweak interactions. No fermions for now, only the gauge bosons and the Higgs boson. And the coupling between the Higgs boson and the gauge boson is hidden inside these covariant derivatives. And the Higgs boson has one special property in that it has a non-zero vacuum expectation value. And one consequence of this is that you can plug in this vacuum expectation value in this term in Lagrangian, and you end up with a mass matrix for the gauge boson. And if you would like to find the eigenvalues and eigenvectors for this mass matrix, we can always change basis to the mass eigenset basis. And this is, of course, well known how to do. So you just change your gauge field to this other set of gauge fields using this rotation matrix here. And as a consequence, you get the masses for the W and Z boson, which depends on the gauge couplings and the Web. Yes, but we want to deal with an effective field theory. So let's just extend the standard model in the usual way, including high dimensional operators, using the same field content as in standard model and the same symmetries. And these high dimensional operators now have their own independent Woodson coefficients. And in particular, if you focus on dimension 6, the story I just outlined about how to go to the mass eigenset basis now changes. So there are 3 new operators which have an effect. And you can see this from, if you just imagine that the Higgs fields here take on their vacuum expectation values, these operators now affect the kinetic term of the gauge bosons. This is, of course, well known a long time ago and was solved there as well. So the solution now is to redo the calculation of the mass eigenset basis in 2 steps. First, you want to canonically normalize your gauge fields, and then you want to rotate to the mass eigenset basis. And now things get a bit more complicated. So first of all, in this canonical normalization step, you can absorb this normalization into the gauge couplings. So all the gauge couplings will have these bars, which just means that they have absorbed these normalization factors. But on top of that, these rotation angles, which in a standard model was just a simple ratio of gauge couplings, now you get this additional term from the CHWB operator. And as a consequence, the masses of the gauge fields also change, now with bars, just to indicate that they're in the standard model EFT and not just the standard model values. And we see that the Z boson have barred couplings, and it has the CHWB term, and there's a CHD term as well. You might say, okay, fine. It's a bit more complicated, but it's not too hard to handle. But let's just turn the crank. Let's see if we can go to the mass dimension 8. And this is also really relevant because recently the operator basis at dimension 8 has been written down by and talked about in this conference. So at dimension 8, there are now 4 new operators which are relevant, namely these guys. And you might say, okay, let's try the same solution as before. Let's canonically normalize the gauge fields and then rotate to the mass eigenset basis. So you have to redo all these steps because, because there are dimension 6 squared effect, which you didn't keep track of from before. And you might start to wonder whether this is the best strategy. Just as an example, this Lagrangian parameter, this rotation angle, in a standard model, it's very simple. It's just this ratio of gauge couplings. Then you have to bar all the gauge couplings. And then at dimension 6, you have to add this CHWB term. And if you go to the mass dimension 8, there are now dimension 8 operators which enters, as well as these dimension 6 times dimension 6 operators. So you can see that this is just one example of many parameters you have to calculate and work out in detail. And it gets very complicated very quickly. So let's just see if we can approach this problem from a different angle. And so let's just write down all the operators which affect the kinetic terms of the gauge bosons. Namely, we have the 2 in the standard model and the 3 at dimension 6, and then at dimension 8, and so on. And instead of writing them out one by one, we can just group them together into one term, where we have 2 field strength sitting out back, with the full component as the B field, and they're connected through this GAB matrix. And from one point of view, I haven't done anything. I've just rewritten the terms into one term. But from a different point of view, this is conceptually illuminating, because what this looks like is a metric. But it's not a metric in space-time. The indices are not space-time indices. It's a metric in field space. And I'm glad that Nathaniel talked about the same concept, because it's really the same as what's happening for the scalars, where you have the kinetic term for the scalars being connected through a metric in field space. What's different here is that now it's really the gauge bosons which have their own metric. So I'll call this GAB the gauge field space metric. And one consequence of this is that we can look at these all algorithm going to the mass angular basis. So before it was this 2-step process of canonical normalization, then rotating, and you have to work out all the different parameters one by one, and it's kind of hard to keep track. In this new formalism, you just do a simple transformation in one step, given here. So you have this rotation matrix, U, but also this metric makes an appearance in this transformation. And what's more, direct consequence of this transformation, just based on consistency, lead you to very simple, very closed form expressions for all the gauge couplings. So you have the G2 bar, the E bar, and the GZ bar now only depend on the gauge couplings in the original weak eigenset basis, plus this gauge field space metric. The same is for these rotation angles, only depends on the couplings in this metric. This is additional theta z angle, which was not there in dimension 6 or in the standard model. This is just what's in the covariant derivative for the Z boson. And you can see that these expressions are the same in the standard model and dimension 6, but they differ at dimension 8 and higher. That's why there are 2. And lastly, the masses of the gauge bosons have a very simple closed form. The only thing with the masses is that there's also this H11, H33 object showing up. But not to worry, that's really just more of the same. This H object is coming from just the scalars themselves. So we can do the same thing as before. We can look at the kinetic term of the Higgs field, and then we can add all the 2 derivative terms with only scalars, and then just regroup them into this 2 derivatives on scalars out back connected to this Hij metric. And this is really the same thing that Nathaniel was talking about. It's the same looking field space metric, but now for the scalars. So now we have closed form expressions for all the Lagrangian parameters who know how to go to the mass angular basis. We can also write down explicit expressions for these field space metrics. And this is based on Hilbert series counting. So we heard Tom previously in this workshop talk about the asymptotics of the Hilbert series, which enumerates all the operators in a given EFT. And this is like an exponentially growing number. So you might worry that there are like an infinite number of operators you can write down which are relevant. But it turns out that there's, for this specific set of operators, the number is quite low. And for the gauge fields, there are 3 at dimension 6, 4 at dimension 8, and 4 at dimension 10, and so on. So it just stays at 4. You can always add like an H dagger H out front, but you can't there's no new structure that appears beyond dimension 8. And because of that, we can just write down a complete all-order expression explicit for these metrics. And the nice thing is that then you just take this expression, plug it into all the Lagrangian parameters, and expand if you want to work out dimension 8, say, or dimension 10. And you have the expression there. Good. So let me now focus on a different aspect where geometry shows up, namely in on-shell amplitudes. And this brings me back to the point I raised in the beginning, that should you use amplitudes or should you use fields and Lagrangians? And I think maybe the sweet spot is somewhere in between. So just look at, for example, a sigma model, by which I mean two derivative scalar theory, where these ij can enumerate either flavor index or just like keeps track of the various scalars. So this can be written compactly in this form, where this Gij now is the field space metric for these scalars. And if I asked you to write down, from just using on-shell amplitude techniques, write down the 4-point amplitude, you would look at the kinematic considerations and find that it consists of two independent Mandelstam variables, this SAB and SAC, and they're independent, so they will be assigned their own independent coefficients. And without any more inputs, that's really all you can do. But if you calculate the same object from this Lagrangian, where you have this field space metric, what you'll find is that the coefficients, C1 and C2, really are curvature invariants. These are the Riemann curvatures from this metric. So you see that you learn something about these coefficients now if you combine the geometry picture with the on-shell picture. And this extends to higher points. You will find that it will become curvatures acted on with some covariant derivatives and so on. So all the coefficients will be curvature invariants. And now we can go back to our original example of this non-factorizable part of two gluons and two scalars. So we have different kinematic variables. We have these spinor products. But if we focus on this A1 coefficient, we'll realize that the relevant field space metrics are now given below here. It's the same as before, but now they're gluon field strengths as compared to electroweak field strengths. But other than that, it's the same story. And this KIAB and tilde KIAB are these field space metrics, which can now be written down at all orders in the EFT expansion. And if you then again do the calculation of the on-shell amplitude, you find that this coefficient A1 is simply given in terms of these field space connections and curvature invariants, even for the gauge bosons. Another example is the Higgs to two-photon coupling, relevant for phenomenology, of course. So from the on-shell amplitude approach, is just given by the spinor product times coefficient B1. But this B1 can now be related to the gauge field space metric in this way. And the three various terms is simply coming from this rotation to the mass signs basis we talked about before, as is the E bar couplings that show up. Good. And the last thing I wanted to just discuss briefly is some application of this formalism to phenomenology. So you might say, okay, this is all nice words, but how can I use it? Can I use it to something relevant? And in fact, you can. There are a number of observables which have been written down to only depend on these field space connections. One example is the Z boson decaying into two fermions, given by this expression here. And a lot of the heavy lifting is done by this G effective coupling, where the G effective coupling depends on the G set bar coupling. Also this theta set coupling or angle we had before, as well as this L object at the end. So the only new thing is this L, which we haven't seen before, but not to worry, this is really just more of the same. It's not a metric anymore, but it's something that in spirit can be constructed the same way. So just take all the operators with 2 fermions in this combination and 1 derivative on a scalar, and then just like dump all the rest of the scalars into this function out front. And for the same reasons as for the metrics, the number of operators that enter here is limited, and because of that, you can write down an all-order expression for this this connection. So with this in hand, as well as the metrics and Lagrangian parameters we had before, we can now calculate this ZDK to as high in the mass expansion as we want. And if we want some numbers out as well, we have to use some input parameter scheme to relate Lagrangian parameters to numbers. And this has also been done using these geometric objects. But I'll not explain the details here. One example of what this helps with is that we can now answer questions we couldn't before. So back in the day, we were only able to calculate up to dimension 6 in the standard model, partly because we didn't know the full basis at dimension 8, which has now been recently solved. And if you only have dimension 6 correction to your amplitude, you might wonder, okay, should I keep the dimension 6 squared corrections in cross sections and decay rates, which take the square of the amplitude? Or is this a good representation of the dimension 8 effects in general? And now we can just simply answer these questions by plugging in the numbers. So for this G effective coupling, we can relate it to use the input parameters to get some numbers out. We have the standard model value there. We have that linear in dimension 6. And we also have the full dimension 8 corrections here. And then you can just compare whether dimension 6 squared is representative of dimension 8 times the standard model or not. And in general, it's not. Maybe it's not too big of a surprise, but it's just nice to see. But the upshot is that now you can just include as high accuracy as you want. You can just plug it into these formulas and expand up to the desired accuracy. So with that, I'll just summarize briefly some advantages of thinking in terms of this geometric field space. First of all, we can define the metric and other connections to all orders in the EFT expansion. We can relate all of the Lagrangian parameters using the field space metrics. The same is true for the input parameters. I didn't discuss it here, but I've discussed it in previous HEFT conferences that this geometry also enters in gauge fixing. And if you gauge fix that way, you end up with very simple word entities using the background field method. And one thing which I think is pretty cool and underappreciated is that the coefficients in on-shell amplitudes are curvature invariants, so that it sort of begs for a union between on-shell methods and this geometry methods. And lastly, this is also very practical formalism, because you can just take a lot of expressions for a lot of observables and plug in numbers, or expand and then plug in numbers, and you can then more directly relate those to observables and experiments. So with that, I'd like to thank you for your attention.
Okay, thanks a lot for a nice talk. Questions from the room? Oh.
Hi. I guess one of the beauty of modern on-shell amplitude method is you can forget about the Lagrangian. Now it seems that if you use the on-shell method to write down the amplitude, you have to use the geometric, the metric to obtain the coefficients as you discussed. And to obtain the coefficients using the metric, you have to know the Lagrange in the first place. And this seems you lose the beauty of the on-shell method, right?
Well, I would put it around. I would say that if you combine on-shell method and this geometry, you gain more beauty because it's you can both have the on-shellness and you can have some geometry things. But I think the point is more that it's not wrong using just on-shell methods. You'll get correct answers and you just parameterize by these coefficients, but you don't gain the insight at what these coefficients mean.
I see. But let me ask another question. In principle, you can. In principle, could you fix the coefficients by just using the on-shell method? I remember we can do this, even though we may lose the understanding of the meaning of these coefficients as you did in the metric way. But I think we can still fix these coefficients using the on-shell method.
Yeah, sure. You can always fix it to experiments. That's not the issue. But I think it's hard to sort of reconstruct these curvature invariants just from the metric. In that, like, just from on-shell amplitude, I would say, in that it's the expanded version of the Riemann that shows up in the amplitudes. So you had to somehow resum a whole series of on-shell amplitudes in order to regain the full Riemann, for example. But you can try to do that as well, and then you can say that the information is equivalent.
Thanks.